Hello everyone, welcome back to LMJ. Today I am back with another video. This is the part 1 of NSEP PYQ solutions of the chapter Work Power Energy. So let us start with the first question. So it says that an elastic spring of unstretched length capital L and force constant K is stretched by a small amount x. It is further stretched by a small amount y. So the work done in the second stretching is asked. So initially the spring is something like this, that this is the original length, let us say L naught, sorry, L, it is given as L, and in the first stretching it is being stretched by an amount x, right? And in the second stretching this is L plus x, and this string is being stretched by a small amount y. So this is the condition of the spring after the second stretching. So we know that the force of the spring is given as minus kx, right? Because the spring force is in opposite direction to the direction of stretching, so we have put a negative sign. But to calculate the work done in stretching the spring, we need to calculate the work done due to the external force, which would be the negative of this minus kx, right? The external force is negative of the spring force because we can assume that at every point of the stretching, the spring is the spring has no acceleration. Basically, the spring is at equilibrium at every point of the stretching, so it is being stretched very slowly. So there should be no external forces. So external force should be equal and opposite to the spring force. So now we need to calculate the work done by this external force, and this is not constant, so we cannot directly multiply it with the displacement. Since this is varying with x, so we need to take the integration. So force multiplied by small displacement dx. So initial stretching is x and final total stretching is x plus y. Don't take this as y, because the final x coordinate is x plus y, right? If we take the L as the origin, here is the origin, so this coordinate is x plus y, right? And x is the coordinate, so this will become kx square by 2 from x to x plus y. So this will be k by 2 x square plus y square plus 2xy minus x square. So minus x square and plus x square get cancelled, so we are left with k by 2 y multiplied by y plus 2x, which is equal to the option D. So moving on to question number 2, it is a 3-marker from 2005. It says that a particle of mass small m is executing oscillations about the origin on the x-axis with amplitude a. So this is the origin and the particle is executing SHM. So this is the origin and it is executing SHM on the x-axis. So this would be a comma 0 and this would be minus a comma 0. Potential energy is given by a x raised to the power 4, where small a is a positive constant. The x coordinate of the particle where the potential energy is 1/3 of the kinetic energy is. Okay. So this is a nice question. So let us see how we will proceed. So we know the expression for the potential energy, and we need to find when the potential energy is 1/3 of the kinetic energy. So since we have to relate both potential energy and kinetic energy, we'll need to find the total energy first. And we can do that since we know that at this extremum, the kinetic energy is given as 0 because the velocity is 0, because the particle will be changing direction of motion here, right? Particle is going in right direction first, and once it reaches this point, it has to move in left direction. So the velocity will change from positive to negative and it will cross 0 in that process, right? So at this point velocity is 0. So total energy is equal to potential energy plus kinetic energy, and kinetic energy is 0. So total energy is consisting only of potential energy at the extremum. So, and potential energy we know it is A multiplied by x raised to the power 4. So total energy will become A multiplied by capital A raised to the power 4. Right. So now we know the total energy, and we need to find when the potential energy is equal to 1/3 of kinetic energy, which basically implies that kinetic energy is 3 times of potential energy. So again, using the total energy formula, I'll put kinetic energy as 3 potential energy, so it will become 4 potential energy. So A multiplied by capital A raised to the power 4 is equal to 4 times of small a x raised to power 4. We need to find the x, right? Where this x is the position where potential energy is 1/3 of kinetic energy. So A and A get cancelled. So we'll finally have A raised to the power 4 by 4 is equal to x raised to the power 4. So x will be A by root 2 plus minus, right? So this was a decent question, and the answer is option B. So question 3 says that a particle free to move along the x-axis has potential energy given by k times 1 minus e raised to power minus x square for x belonging to minus infinity to plus infinity, and k is a positive constant. So we are asked certain questions related to equilibrium, unstable or stable equilibrium, and also the nature of force, and if the motion is simple harmonic motion. So this is a multi-option correct question, and this is a nice question. This kind of question is quite common in JEE nowadays, so you must have attempted these kind of questions. So let us look at the solution. So U, the potential energy as a function of x, is given as k times 1 minus e raised to power minus x square. So we know that at equilibrium the force is equal to 0, right? That is the condition for equilibrium. And we also know that force is equal to minus du by dx. And at equilibrium, force is equal to 0. So we can find the points of equilibrium by equating force as equal to 0. But first we need to find the equation of force. For that we'll do du by dx and put a minus sign. So force is equal to minus of this k times 1 will give 0 on differentiation, and this will give, so minus times minus 2x will be plus 2x e raised to the power, there is a k also, so e raised to power minus x square. This is the force, and it is 0 at x is equal to 0, right? If we put x is equal to 0, then this force will become equal to 0, and I don't think at any other point you will get an equilibrium point. So hence x is equal to 0 is a point of equilibrium, right? Because at equilibrium force is equal to 0, and at x is equal to 0 force is equal to 0. So x is equal to 0 is a point of equilibrium. So if we see option A, it says that a point at points away from the origin, the particle is in unstable equilibrium. No, this is not wrong, because at points away from the origin, there is no equilibrium. Equilibrium is only at the point of origin, and no other point has equilibrium. So A is definitely wrong. We don't even need to check the if it is unstable or stable, because there is no equilibrium at when x is not equal to 0. So now for any finite non-zero value of x, the force is always directed away from the origin. So if we see, force is equal to minus k times 2x e raised to power minus x square. So if x is positive, then force is negative, right? because k is positive, this term is positive and 2 is positive, so there is only a negative sign, so force is negative. Hence, force is directed towards the origin. And if we see for x is equal to negative values, if x is negative, then force is positive, and see, if x is negative, it will be somewhere here, and force is positive, so again it is pointing towards the origin, not away from the origin. So again we can say that force is directed towards origin. So B option is also wrong because it is saying that force is away from the origin, but it is towards the origin. Option C says that if the total mechanical energy is k by 2, then it has minimum kinetic energy at the origin. Let us see this. So we know that total energy is equal to potential energy plus kinetic energy, and at origin we already saw that at origin we can see that this potential term will become 0 because e raised to power 0 is 1, so 1 minus 1 is equal to 0, so potential is 0 at x is equal to 0. So at x is equal to 0, which is the origin, potential energy is equal to 0. So the total energy is comprised only of kinetic energy, right? And it is given as k by 2. So this implies that the kinetic energy is maximum at origin, because at any other point there will be some potential energy, and so kinetic energy will be that k by 2 minus that potential energy, so it will be less than k by 2, but at origin it is k by 2. So this implies that kinetic energy is max at origin. So option C is also wrong because it is saying that at origin the kinetic energy is minimum. Now option D is asking that for small displacements from x is equal to 0, the motion is simple harmonic. So let us see. Uh, so we know that for motion to be simple harmonic, the force should be proportional to x, right? So we know that the force equation is, we derived it, minus 2kx multiplied by e raised to the power minus x square, and we need to find if at small displacement from x is equal to 0 this is a simple harmonic motion. So currently it is not looking like simple harmonic motion because it is proportional to x and there is also e raised to power minus x squared, so it is not directly proportional to x. But we can eliminate this term for small displacement from x. We'll see how, because we know that by Taylor series for small x, the expansion of e raised to the power x is given as summation of from n is equal to 0 to infinity 1 by n factorial x raised to the power n. So this basically means that ex is equal to 1 plus x plus 1 by 2 factorial x square plus 1 by 3 factorial x cube and so on. So this e raised to power minus x square can be written as 1 plus x is minus x square, so minus x square plus 1 by 2 x raised to the power 4 and so on. So force will become equal to minus 2kx plus 2kx cube and so on. And if we ignore higher order terms, because if x is very small, displacement from 0, so x will be like 0.0001, and x cube will definitely be smaller than x, right? So we can ignore this term because it will be much smaller than x, because 0.0001 raised to power 3 is much smaller than 0.0001, right? So ignoring higher order terms, we get that force is equal to, sorry, it can be approximated as minus 2kx, which implies that force is directly proportional to x, which implies that the motion is SHM. And we can also find the angular frequency, so it will be 2k by m. So option D is correct here. So this was a nice question, and now we'll move on to question number 4. So moving on to the fourth question, it is a 12-marker question from 2005. It says that a pendulum bob of mass small m is raised to height h and released if it hits a spring which gets compressed. So if the spring is following this non-linear force law, then we have to show that the compression length would be this in equilibrium, right? So this is a fairly straightforward question, but many people can make some calculation errors. So firstly, the ball is raised to some height above the spring. So when the ball will come down, it will lose some potential energy, because the potential energy here would be greater than the potential energy at this point. And the potential energy lost by this would get transferred into this spring, because initially also the ball is at rest. We'll assume it to be at rest, and finally it is also at rest, because only x is asked and there is no mention of any velocity. So it means that all the potential energy due to gravity has been transformed into the potential energy of the spring. So the initial potential energy, if we take this line as the reference line, then the initial energy can be written as mgh, right? The potential energy due to gravity, and that is getting transformed into the potential energy of the spring. Now notice that this is not the normal Hooke's law or linear force where F is minus kx, so we cannot use the formula that we have learned of half kx square. We need to derive the new formula for this non-linear force, and for that we'll turn to our basics. So the energy stored by the spring, this can be given as, if we integrate this multiplied by dx, so force multiplied by the small displacement over the entire displacement, since this is not constant with x, so we need to integrate it. So from 0 to x, and there would be a minus sign also, because the potential energy is getting stored in this, right? So this is negative of the work done by the spring. The energy stored in the spring will be negative of the work done, right? So minus kx minus bx cube dx, which would give us kx square by 2 plus bx raised to the power 4 by 4. So the initial and final spring energy should be equal, right? Because this gravitation potential energy is getting converted into the spring energy. So equating mgh to kx square by 2 plus kx raised to the power 4 by 4, we get, I am taking the LCM, so 4 mgh is equal to 2kx square plus kx raised to the power 4. Now this is a biquadratic equation and we need to find the value of x, so we will put x square as t. So this equation will become kt square plus 2kt minus 4 mgh, and we need to find the roots of this equation, right? If I take this on the LHS, so 0 will be here and we need to find x. So this is basically like finding the root of this equation and then taking the square root, because t is x square. So I'll use the quadratic formula. So T will be equal to minus 2k plus minus 4k square plus 16 b mgh by 2b. So cancelling out 2, if I take out 4, that will become 2. So T will be equal to minus 2k plus minus k square plus 4b mgh by b. Sorry, this 2 will get cancelled. So from here we have gotten the value of x square. So x, this was x square, right? So x will be square root of this, right? K square plus 4b mgh divided by b. So now to write it in the form which is given in the question, I will divide this whole thing by b. Basically take this b inside the square root, so it will become x is equal to 4 mgh. So if it will become b square on taking inside the square root, so b by b square is 1b in the denominator, and this will be k square by b square whole raised to power half minus k by b raised to the power half. So notice that I have removed the minus sign. I have taken only the plus sign, and minus sign I have cancelled because if you see, if I minus this thing from k, it will become a negative value, right, inside the square root, and square root cannot have a negative value inside it. So I have considered only the plus value here. This will be the final answer, and this matches with the expression that is given in the question. So moving on to the next question, question 5. It says that a windmill converts wind energy into electrical energy. So if V is the wind speed, then we have to find the electrical power output. Okay. So let us consider that the windmill is something like this, right? I made a circle to show the area covered by the wings when they rotate, right? This will be something like this. So consider that the area of this oval thing is A. So the wind is moving into this windmill, right? And the particles inside the wind will collide with the blades of the windmill, and it will start rotating and convert into electrical energy, right? So the wind will be considered of many small particles, and consider that the density of particles in wind is equal to rho, and cross section area was A. So what is power? Power is the energy produced by this windmill every second. So for that we need to find out the energy of individual particle, and then we need to multiply the energy of individual particle with the number of particles passing through the windmill every second, right? So first we'll find out the energy density, which is equal to the energy of one particle, right? So this will be equal to half into v square, right? If we have considered the mass of every particle to be 1, or let us say m, okay, so half mv square is the energy of every particle of mass m, right? And number of particles of mass m passing through windmill every second, because power is defined as the energy of the all the energy produced in 1 second, right? So we have to find out number of particles passing through windmill in 1 second. So that will be equal to the number of particles in air, which is rho. The number of particles in unit volume is rho, and the volume passing every second would be equal to velocity multiplied by area, right? Because this gives us the length covered in 1 second, and area multiplied by length covered in 1 second will give us the volume covered in 1 second, right? So this gives us the number of particles in 1 second. So power would be equal to half into mv square multiplied by rho va, which is half m rho a v cube. So power is proportional to v cube. So the answer should be option C. This was a nice question, but this is quite common nowadays. So hope you enjoyed the part 1 of work power energy solutions. I'll be coming up with new videos more regularly now. So don't forget to like and subscribe. Thank you.